thank you very much for all the organizers of the conference. It's a pleasure to be here and to be invited to give this talk. I'm going to talk about this common project with Samuele and with Eran Asaf. Well, my policy is that if the person is here, I use the first name, and if the person is not here, I use the last name to mention them. I don't know if I'm going to be coherent with all this, but I'll try. So, I mean, it's weird to say, like, we do it in papers, right? Like to write, like, we thank this grant or this whatever. I'm going to kind of do it in a talk, not the grant, that there is a grant that somehow pay for this. But I want to thank John Boyd, I have to say the name, and Kiran Kerlaya, that were two of the organizers of actually the conference where like this project started on. And I mean, I want to say this to thank those people because somehow I want to put the value on the work that people do organizing events, which is very good because, I mean, help us to meet other people and to discuss and then to get like projects started. So, I mean, that was an example. During that conference, the name of the conference actually was Arithmetic Aspect of Explicit Modular Problems that happened in Banff in 2017. So, I mean, there was like these open questions, you know, 1 hour, everybody asked whatever they want. And at that moment, I was working with a smooth plane models, and there were people talking about modular curves. So I asked my question, like, do you know if there is like some modular curves like as meeting a smooth plane model, or how many do that? And then Samuele came to me and told me, oh yeah, I have some ideas about it. And then actually John came to us like sometime later saying, hey, I have a postdoc that is working on something that can be helpful. And well, I mean, this person was Eran, and then I mean, it worked and we got the result. So let me start, I mean, even if I think that everybody knows, but I'm going just to start with the definition of what it is a modular curve. Just for sake of completeness. Definition, decompactification. Well, by normalization, by adding the cusps when needed, of the Gaussian space well, the upper half plane, by the axiom of a congruent group gamma in SL to Z is called a modular curve. So, I mean, I guess that all of you already knew what was a modular curve. I just mentioned that modular curves, they are defined in this way. They are smooth, algebraic projective curves because of the work of Shimura and Serre, that we can also say something about the field of definition. They are defined over Q of primitive root of the unity. The order of the root of the unity is related with the level of the modular curve of the congruent subgroup. So those are the objects that we want to look at. I insisted on giving the definition because I don't want you to get confused with modular curve and a curve that is modular. Okay, a curve that is modular is dominated by the x1n. Okay, so I mean, for me, modular curve, this is a meaning. Many people, lot of people really, I mean, I think that I don't have to convince you, like in this community, about the importance of modular curves and about computing equations of modular curves. There has been a long history about people computing equations of modular curves. So just let me mention some names. So let me mention Galbraith, of course. In the 96, plus many other people, they developed techniques to compute equations of modular curves, in particular, for instance, for the x0n. So two things about this. One, of course, is via modular polynomials. But you know that if you do this, you are going to get like very huge equations. They are plane models, but they are not smooth in general. They are like highly singular. And then the coefficients are huge, but well, I mean, anyway, you get equations. But then, and actually this is somehow the technique that we are going to use in this paper, the idea is that if you look at two-weight cusp forms, then you have like a relation between these cusp forms and the regular differentials of the curve, and then you can work to compute the canonical model. So, I mean, this is the approach that we will use, because, I mean, of course, I want to compute like some modular curves with some special properties, and the way to get the model is going to be via canonical models. Canonical models. So let me also mention the work by David Coel. I think that there are several Davids here. So I mean, this one is very different. It's via quaternion algebras. And I mean, this was useful because there is like a small database with a lot of equations of those curves. Things are implemented in Magma. Many other people computed equations, but now let me say something more about the applications, possible applications about having equations for modular curves. So maybe I'm not going just to write everybody's name, but there is this paper by Baran in 2010, Dose, Mercury, Stirpe 2017, in which they compute some equations of modular curves, and it was useful in order to address Serre's uniformity question. That was a thing, not conjecture. Uniformity question. There are some works of Freitas, Lehun, Zygzek, again Zygzek with Derricks and Neyma, Philippe, that is around here, to use modular curves to study modularity of elliptic curves over real quadratic cubic or cubic fields. Here, modularity in the other sense, not that one. Then there are also like some works by Van White and John Cremona from 2014, and also by Siwina from 2021, in which they use like explicit computation of equations of some modular curves to study a failure to local global principle, of L isogenies. I also have a paper with a student in which we use like modular curves and computation of their twists and the modular interpretation, also to study like a failure to local global principle, but of the curve, not of the L isogeny. So like, I mean, you know, like getting equations of modular curves is interesting for many reasons, and people have been doing it for a long time ago. So more about the equations, and now I mention this algorithm because it's the algorithm that we use in this work to compute equations of modular curves. So it's the algorithm by Box from 21. Well, there is kind of a generalization of this algorithm also by, or some ideas by Siwina. Well, I mean, the years of the publication then is different from when the results came up. So I'm going to say more about the algorithm. It's the algorithm that we are going to use in this work. This algorithm that was like a theoretical algorithm that is now implemented by my co-author, Eran. So it's plus Eran, Asaf, 22, so it's quite new. And basically this algorithm, well, I mean, it's basically based on Galbraith's idea of using the canonical model. So we just compute weight 2 cuspidal forms. And basically the algorithm is the following. It works for groups gamma with surjective determinant we ask minus identity to be in the group, and the group is normalized by conjugation by this matrix. Well, those are some technical conditions. Let's say that the first technical condition, the surjective determinant, this is just kind of equivalent to ask that the modular curve that you're considering is defined over the rationals. And then this is a technical condition for the algorithm to work. So this algorithm is very good because it allows to compute equations for the modular curve x gamma, but it also works to compute equations, and we'll use this explicitly in our work, to compute quotients when you take a subgroup of the automorphism group of the modular curve, we can also get a quotient of this curve by using this algorithm. We have to be careful because the idea, as I said, is that you take the way two cuspidal forms. So this is equivalent to looking at the differential, differentials. So then you have to look for the relations. So those are the equations defining your curve. You have to look for those relations, but in order to prove that those relations are really given equations of your curve, you have to check like how many terms of the Q expansion of your form you have to use to get something that is proven to be right. But well, I mean, the algorithm works. So, I mean, this is not the computational part that I want to focus today. Yes?
So it's surjective onto where? These subgroups of GL2 Z mod N?
Oh, yeah, I didn't write into them, but yeah, and I don't have it here. But it's, yeah, when you look at the determinant and you have fixed the level, I'm actually going to give the definition of the groups we're working later, but in set N set star. N, capital N, the level of the subgroup. Okay, very good. So maybe I'm just going to give, now that we have this, because of course in the title of my talk, you see that I'm working with modular curve of Shimura type. So maybe I'm going to give the definition of Shimura type, so we all know what we are talking about. And then I will motivate, I have to use, why we use that family of modular curves, let's say it like this. So leave this here. So definition, modular curve of Shimura type of level n. So this is a group. So basically I have to, this is going to be a type of modular curve. So I have to tell you the congruent subgroup, like which conditions does it have to satisfy. So basically we denote it by this, and now I will say who is H and who is T. And this group is basically the pullback to PSL2 of a subgroup G8T, basically containing matrices like this. Where A is in 8, that is a subgroup of here, and T divides B, where T is a divisor of N. So you get such a subgroup, then you do the pullback. I always get confused with this. No, push. PSL2, SL2, push 4. Pushback. Pullback. Well, you understand what I mean, right? Like you go in this direction. So this is the family that we will work, and we'll see later why. But somehow, just starting by, this is a family that we can apply this algorithm, so we can compute equations. So this is important thing. Okay, so now I'm just going to state the theorem, the main theorem in our paper. I can do it now. We have the ingredients. Theorem, Annie, Asa, and myself. So that's the title, so you know now what is the question that we are looking at, okay? They are a finite number of modular curves admitting a smooth plane model. And in such a case, if such a model exists, we can prove that the degree of such model has to be less or equal than 18. So, I mean, here still I haven't said anything about Shimura type. This is coming later. Because, I mean, of course, like the goal is to characterize all such modular curves admitting such a smooth plane model. So the first result in this direction is that we can prove that there is a finite number of them. I'm going to give the proof now of this theorem. And then, of course, once that we have proved that there is a finite number of them, what is the idea? Oh, let's compute them, right? And well, we'll see the problems that appear there. Yes?
When you say finite number, you actually also know which ones they are?
Yes and no. I'm going to develop the question. We know something.
You're pulling back something from a GL2 setting to an SL2 setting? Is it determinant 1 or is it not 1?
So basically, when you have this projection, right? PCL2. So I have something that lives here, and then I want to put it here. So I want to define this thing. It's the image, right? I'm making my life very complicated. It's just the image.
Your GHT is GL, it's not SL, right? Or is it?
Sorry. Yeah, so I mean, this is just, I wrote it here, is from here. So we have the group here, and then we consider the image.
So what about the survey?
It's a projection.
So which way does the arrow go? You're mod n, and then you lift, and then you project?
Yes.
And what about the subjective determinant if you're in SL setting?
Okay, no, okay. No, you're right. I have to consider GL2.
I mean the SL setting.
And then, no, you're right. This is why it's more complicated. Because you start with GL2. Now you go to PGL2.
GL2 is what?
No, N. No, sorry. No, set. We want a congruent subgroup, right? I mean, we want something in here. I have to do the intersection. You are totally right.
In the SL2Z setting, that's in analytic setting, it's SL2.
Wait. So you can do the projection from here to here, right? Yeah, no, wait, but this is going to be fine. So, I mean, in general, you can write matrices in general here, right? But now, I mean, I take this subgroup here, the G, that lives in here. This, I define it, the matrices are here. So it's here.
How can you lift something to an SL2 or GL2Z setting into determinant is not 1?
This is here. Now I take everything that is here, such that when I make the projection, I get an element of the subgroup that I have here. Okay? Yeah, and then what you get here, I mean, you get a big thing here. Now you make the intersection with SL2 set. So this gives you a congruent subgroup. That I'm not going to prove it. But this gives you a congruent subgroup. Well, I mean, no, it's easy because it's finite index. So you get this congruent subgroup, and then you say that for all these subgroups, you have something that is called of Shimura type. That's the definition. So this is why, I mean, it's not that easy to write it in one line. Anyway, the theorem, let's look at this first. This is general. Okay, so there is a finite number. It doesn't matter which type of groups. This is the first thing that we can prove. And then, I mean, this is the proof that has to be in every talk. So I'm giving to you the proof. The proof is easy. The difficult part is actually determining which ones are the groups later. So basically, the proof for this is just looking at the gonality. Next talk is about gonality of modular curves, so this is very related. So basically, we know that for a smooth plane curve, this is the genus in terms of the degree for a smooth plane curve. And then we know that for a smooth plane curve, there is a formula for the gonality. So the gonality is just the genus minus 1, right? But then, after Punen, we also know that for modular curves, we have that the gonality is greater or equal than this in terms of the genus. So if you take this formula for the genus, you plug it here and you put it in the inequality, then you get the bound that I'm telling you in the theorem. We can also, but I'm not giving the details, we can also play with some inequalities to bound the level of the congruent subgroup that you have to consider. So we have some bounds, and with that, we somehow managed to make kind of a list of the possibilities. I'm not writing on the list here, but like the possibilities that you get for the congruent subgroups. So let me write a degree of the plane model, genus, how many congruent subgroups you have, how many of them they have real type and surjective determinant, and how many of them are of Shimura type. So I mean, I'm not writing all the table, but so degree 1 and 2, you will see this is easy because this gives you a P1, okay, and actually there is a rational point, so I mean, this case is not interesting, you just get a P1, you have a plane model. Degree 3, 4, so this is going to be genus 3, 6. In general, congruent subgroups, we have some of them. Let me say that also, I mean, after this theorem, okay, there is a finite number of them. Well, I mean, and I didn't say the most important part is that we get here like a bound for the degree, but now there is a finite number of modular curves of a given genus. Like this is the last thing that was missing to prove the theorem. And we can list them. There is a work by Cumming and Pauli from 2003, and basically they give an algorithm to list the congruent subgroups of a given genus, and then there is a website where they make the computations, and you can find that list for genus smaller or equal than 24, which is great. Well, it's great, not for our purposes, but it's great that you have such a list. Not for our purposes in the sense that we have to go up to degree 18, and degree 18 is genus 136. So, I mean, there are actually like many congruent subgroups and many modular curves to check, actually, if they have a smooth plane model or not. So, I mean, we can get like some bounds, but if you really want to list all congruent subgroups up to degree 18, so genus 136, even with the levels that we get, like the logarithm of that number, the bound that we get is the logarithm of that number, 1,897. So we cannot do that. I mean, like with the computers that we have right now, we cannot check for all congruent subgroups and to compute a model and try to check if we have a plane model. So, I mean, it's not computationally possible. So what's the idea here? We do what we can. We do what we can, and we restrict ourselves to a precise family. And the family that we restrict ourselves is this family of Shimura type. Why? Well, I mean, there are kind of two conditions here that we get is that actually they are Shimura type groups that satisfy the conditions here. So we can use the algorithm. We can compute equations for the modular curve. We can compute equations for the cosines of the modular curve. So this is a good reason. And then it's also in order to restrict a little bit like the family, because computationally speaking, otherwise you cannot do it. So I mean, if you go up to degree 18 that we have there, like you get a huge number. Yes.
Sorry, there's a interrupt. I was getting constitutionality is P minus 1, not P minus 1. Otherwise, it's okay.
Of course. Yeah, of course. I mean, the map is just making like you take 3 and. Yes. So I mean, the thing is that, for instance, here there were 163, 108, and here they are 38. Is much smaller. And if I go up to degree 8, why up to degree 8? Because degree 8 is genus 21, so it's still smaller than 24, so we can look at the list. Then we get here, there are a lot. And here they are only 55. So I mean, those are numbers that we still can say, okay, we can look at all of them. So I mean, this is kind of our objective, to look at these congruent subgroups. These give us some modular curves, and then we want to check if they admit or not a smooth plane model. So now let me say more about plane models, and even a little bit more about canonical models. So this is the moment that I start with the more algebraic geometry part. And well, here is also the computational part that I decided to focus on this talk. So let me recall, well, from a canonical model to a smooth plane model. So basically here the idea is that so far what we got is that there is a finite number of such modular curves. If we focus on Shimura type, we have just a very finite list, let's say, well, something reasonable, list of congruent subgroups for which we can compute a model. We can compute the canonical model thanks to this algorithm. So we have those curves. Another question is like, well, now we have to check if we have this smooth plane model. How do you do it? Like starting from the canonical model. And so for me, that was like the challenge. Like, I don't know, the part that I liked. So let me say something. So in general, if you have like a curve of genus greater than 2, K is the canonical divisor. You consider the Riemann-Roch associated vector space is going to be generated by G elements. Then you define the canonical map of this curve as follows. It's a map that goes from the curve to PG minus 1. And well, you just consider the sections associated to the canonical divisor. So the funny thing about this map is that actually it is an embedding, or is a degree 2 map to P1. Degree 2 map to P1. So in the first case, we say that the curve is non-hyperelliptic. In the second case, the curve is hyperelliptic, but a smooth plane model, or curves that admit a smooth plane model of genus greater than 2, they are actually non-hyperelliptic. So, I mean, basically, we need to check like this case. And even we can say more, is that when we have a smooth plane model, so this is going to be like the connection, if we have a curve that admits a smooth plane model, and then we compose here with the D minus 3 Veronese embedding of the smooth plane model, then we get a map into here, and this is actually the canonical model. So when you have a curve given by the canonical model, so here is like if you have a point, you are going to send it to some coordinates. Imagine that is indeed a smooth plane model, that in this case you have a smooth plane model. Then you consider this composition with the Veronese D minus 3. So this is basically, you send a point, here you have 3 coordinates. So here you consider like a basis for the polynomials of degree D minus 3 in these 3 variables. So I mean, you start with xd minus 3, xd minus 4, y, xd minus 4, z, well, 2 points. And you consider all these monomials. So this is actually the canonical embedding. So if we are working with the canonical embedding and we want to look for the smooth plane model, kind of the idea is to say, okay, if we have a smooth plane model, then actually the embedding that I have here are those things. I have to look the relations, but I kind of know how the relations looks like, in particular because I have the equations of a P2 that is embedding here, plus some extra equations that define the equation of the curve, something like this. You will see that it's not that easy, but this is the idea behind. Let me say that a characterization in order to have a smooth plane model, basically you have a smooth plane model, a smooth plane model for a curve if and only if there exists a very ample, complete G2D linear series. In other words, you are basically looking for a divisor of degree B such that the dimension of the Riemann-Roch space associated to it is 3. And then, I mean, this is precisely, you take the 3 sections and the embedding that gives you is precisely the plane model. So this is a characterization to have the smooth plane model. But then, let me go back to the canonical model because it's the model that we have right now. So let me tell you a little bit more about the canonical model associated to a curve and like the equations defining the equations of the canonical model. So for that, I want to state Netter and Ricker-Petry's theorem. Well, here it depends where you look. The name of the theorem changes. It's not that clear who did what first. But well. So it says that if you have a non-hyperelliptic curve, you call IC the ideal of the canonical model. So it is generated by its elements of degree 2, except in some cases that I'm going to say now. I'm going to state them now, but I mean, this is very nice because basically it tells you that you only have to look at relations of degree 2. So if you want, like going back to the algorithm here, like when you are computing the weight 2 cast forms, you only have to look for the relations of degree 2 of this cast form. And then you look at all these relations, and then with this, you are going to get like the equation of your curve, except in some cases that I'm going to state now. So one case is, of course, when the genus is 3, because then it's a smooth plane quartic. So here it doesn't work, the thing about the degree 2 element. Then the second case is if the curve is what is called trigonal. That means that you have a degree 3 map from the curve to P1. So then in this case, you need to consider all the degree 2 relations plus 1 degree 3 relation. And then you have the equations. And then the last case is when the genus is 6, and actually C is a smooth plane quintic. A smooth plane quintic. And then in this case, you also need a degree 3 relation. With 1 is enough. So those are the exceptions. Okay, so now let's go back to our problem, that is try to enumerate all these Shimura type modular curves admitting a smooth plane model. So, I mean, with this info, we have, well, I mean, the genus 0 cases and genus 1 cases that corresponds to the degree 1, 2, and 3. Those cases are easy. Why? Because in all those cases, we have a rational point. The cast path infinity is actually a rational point. And why is it important to have a rational point? Because if we have a rational point, the genus 0 is actually a P1. So it's a little bit, well, is that a smooth plane model? Well, yes. And for G1, then you have an elliptic curve, so you have a degree 3 smooth plane model. So I mean, in this case, all of them, they have the smooth plane model. It's okay. Now we can go to degree 4 and genus 3. So in this case, we look at the list, and then it's also easy, because basically you have two possibilities. Or the curve is hyperelliptic, or it is non-hyperelliptic, but then it is a smooth plane quartic. And then you have such a model. And I mean, somehow I have to say that that was our conjecture at the beginning, when we started working on the problem. That genus 3, you know, you have the plane quartics, and then it's done. So here, yeah, I mean, we just check. We compute the canonical map. If the image of the canonical map is our genus 3 curve, is a smooth plane quartic, great, we got it. If the image is a P1, then it was a hyperelliptic curve, then you don't have the plane model. So until here, no problem. Okay, next case. D equal to 5, G equal to 6. Maybe before that I do that, let me give some, where do I have it? As an aside remark about the dimension of the moduli space. So the dimension of the moduli space of genus G curves, well, G greater than 1 is equal to this. But now if you look at the dimension of this, so the curves that they admit a smooth plane model, okay? So this is equal, well, to 0 when the G is not of the form of the degree that corresponds. And for the right value is equal to this, D plus 1, D plus 2 divided by 2 minus 9, that we can say that is something equivalent to G. So basically the thing is that the proportion is the same, but you know, like it becomes like, well, it depends how you measure it, but it becomes like each time like more difficult. The codimension is 2G, okay, of a smooth plane curves inside the moduli space. The codimension is 2G. So basically, the larger the genus it is, the more difficult it is that you find that your curve admits a smooth plane model. So I mean, that was a little bit the motivation for us to say, yeah, like conjecture. We stop here. We don't find anything else. Well, I'm not going to say conjecture. Question. We stop there. And also, like the strategy about saying, okay, we have many groups. We don't know, like we cannot like really check all of them. We can only check a few of them. The thing is that, well, I mean, if we start by a small degree, somehow are the places that likely we are going to find these examples. Okay, so now I go back to this case. So, I mean, this case is very nice because this case we can directly use Noether-Enriques-Petry's theorem. In which sense? We compute the image by the canonical map, and then there are like several possibilities. One, we have a hyperelliptic curve, right? Then the image is going to be a P1 because we get a degree to map to P1 in the hyperelliptic case. Second case, we get the curve that we want because it's generated by the two elements, but then it doesn't admit a smooth plane model. And then the third possibility is that when we compute this image by the canonical map, we get a P2. Like if we only look at the degree 2 elements. And you get a P2 because this may happen in two ways. That you are here or here. Like in those two cases, you also need the degree 3 relations. So, I mean, in this particular case, the strategy is clear. You look at the degree 2 elements of the ideal. How did I call the ideal? I see. And then you can get a P1, a P2, or your curve. So in this case, it's hyperelliptic. In this case, it doesn't have a smooth plane model. And then in this case, you have to check in which case you are, in the trigonal case or in the smooth plane quintic. And then you get some examples. So we did that with all the groups that we got. And the funny thing is that in all cases, we basically fall down in this case, except in one. So we were very happy. We said, oh, we are going to find another, you know, like another modular curve admitting such a smooth plane model. But no. Actually, we computed and we fall down in the trigonal case. And now I can give you the equation, and it's even more surprising because it's not only trigonal, it's superelliptic. So it's Galois trigonal, if you want. And the nice equation that we found, and I say nice because it's small enough that I can write it in the blackboard, is this one. So this is a genus 6 curve given by this equation. Corresponds with the congruent subgroups label. Well, this is the name of the subgroup. So this was the only exception, and we find this nice curve. And I mean, I really think that this is very surprising because if you look at the dimensions of the modular spaces, like, I mean, a little bit to get an idea how likely it was. So you get that the dimension of the modular space of genus 6 curve is 15. The dimension of the modular space of genus 6 curve, well, a smooth plane quintics is 12. The dimension of the trigonal ones here is 13, which is indeed like larger than 12, but the dimension of the superelliptic ones of order 3 here is actually 5. So we were like really falling down in this special case. So we were like, come on, this is like magic. We were looking for the smooth plane model and we fell down here. Actually, it's not magic. So now I want to tell you that actually we could have known before because the corresponding congruent subgroup actually has automorphisms. And those automorphisms, they are still acting in the curve. So somehow we could have read this order 3 nice automorphism coming from this nice equation. Yeah, it's the Cummins-Pauli. Yeah, and in the website, you can check it.
So it's 18 the level?
Yes. Yeah. Okay, so until here, we are good. Let's go now to the next case. And the problem is that for the next case, we already have problems. Because for the next case, what is happening? So I can tell you, like, how did we find this? Well, I mean, this was easy, right? Because we look at the degree 2 elements. This is given to us a P2. And then we took just a degree 3 one. We plugged the parameterization of the P2, and then we got more or less this thing. Then we have to put it a little bit nicer. But that was the idea. The idea is to recognize the P2. So our first idea for the next cases in which we only have degree 2 elements is among all the degree 2 elements that you have to recognize the ones that they are giving the equations of the P2. And then the one that is not giving the equations of the P2 is somehow the equation of the curve once you parameterize the P2 and you put it in there. So that was our first naive idea, and actually it's wrong. So first version, archive paper, don't look at it, was trying to use this thing. And I mean, actually it's not such an easy problem because, you know, like this characterization, so I mean, you have basically this section. If you look at the divisor of this section, it's like a very particular one because it's going to be d minus 3 times something. So this tells you that look at the sections, look at the divisor, you want like a point with a higher multiplicity, you put it in 1, 0, 0, you try to make some projections. That was kind of the idea. Actually, it doesn't work. Well, or at least the way that we did it, it doesn't work. So I mean, here I have to thank like the referee of the paper, Wouter Gastrick, that helped a lot and actually suggested a different approach. That is the approach that we took. So let me tell you about the formalization about this new approach. So, I mean, I start with a theorem by Green. So this is from the same paper in which he stated the geometric six-digit conjecture by Green. That is not the Green conjecture, it's related. It's not the famous one, it's another one. And in this paper, he proved that if a curve C of genus G equal to what it has to be to have a smooth plane model, and with D greater or equal than 5, but it's already our situation, has a G2D linear series. We still don't know very ample, but if it has one, then the Kosul cohomology group the following one has dimension different from 0. So the idea is to compute this number, and if this number is equal to 0, then we know that we cannot have a smooth plane model. This number that looks ugly like this, actually is not that ugly at the end, because this dimension is actually equal to this graded Betty number. And I mean, graded Betty numbers can be computed with magma. So this is very useful. I don't want to do publicity of magma here. I'm sure that it can be computed with many other programs. So the idea is that we just need to compute these numbers. So how can we compute those numbers? Oh, well, let me at least tell you a little bit how do you compute those numbers. So the idea is that you just take, I do a parenthesis here. I'm just trying to economize, like, save some space for later. This is why I'm using this part. Yeah, thank you. So the idea is the following. You just take the coordinate ring of your curve. You look at the canonical model. So it's really the setting that we are. We have the canonical model of the curve. So you look at the coordinate ring, and then you take a minimal free resolution. So if you never have seen this, honestly, for me, well, this was idea suggested by the referee, so we look into this. For me, it was actually the first time that I was looking at this kind of strategies, and I have to say that I loved it. So now I'm very into minimal free resolutions. So basically, the idea is that here you have the coordinate ring. Here you have the ring. F1 are basically generators of the ideal, a minimal number of generators that you can get of the ideal. Then the next module is like the minimal number of relations, like the minimal number of generators of the relations of the generators that you put of the ideal, and then you go back like this. And then this can be proved that for a genus G curve, when you work with the canonical ideal, then the length is up to G minus 2. And now, like, if you look at those relations, so six sigis, then you look at the degree of those relations, and I mean, this Betti number is basically related with the number of relations that you have of a given degree in a given place. And this can be computed. So, okay, now this theorem gives us the strategy, right? So the strategy now is to say, okay, great, we compute the Betti numbers. If the Betti number is 0, great, there is no such a model. If the Betti number is different from 0, well, then in that case, you need to check if you really have a smooth plane model. And here, to check if you really have a smooth plane model is to find the P2. That is kind of complicated, as I said, but there is a result by Schreier from the 91, in which he actually proved everything that is known until now of this geometric six-sigid conjecture by Green, in which basically he tells you when you are like in this situation, like doing like some Grosvenor basis approach, you take the right basis of the ideal, how to get the equations defining the P2. And then the other one gives you the equation of the curve. I'm just saying this very fast because actually in practice we never have to use this. But like in theory, like you can do it. Okay, so now with this result in hand, I can tell you, I'm not even going to erase this, I can tell you what happened for the next cases. So the next case was degree 6 genus 10. So in this case, we get 17 groups. Among the 17, for 15, we get that the Betti number is equal to 0, so there is not a smooth plane model. And then for 2 of them, we get that the Betti number is not equal to 0, so a priori that could be such a number. But in those cases, we are able to prove that there is no such a plane model by using something that we call the Aitken-Lerner test. Basically, the idea is because those are modular curves, there are some involutions, Aitken-Lerner involutions. And when you do the quotient but one of these involutions, we get an elliptic curve. So if you get an elliptic curve, then you can say something about diagonality. Because then you have a degree map to an elliptic curve. The elliptic curve has a degree to map to P1. So this gives you a degree for map to P1. And this contradicts the thing that diagonality has to be D minus 1. So then we are able to remove these cases. We call this the Aitken-Lerner test. And then it's fine. And then let me say, and I'm going to finish with this because I have 1 minute if I'm not wrong. For degree 7, genus 15, so I'll do it at the same time, and degree 8, genus 21. And I stop here because the tables only go until genus 24. So these are the things until we tried. We only have congruent subgroups until here. In those cases, we try to compute the Betti numbers. But what is the problem here? Too big. Now I'm going to say something bad about MAGMA. So MAGMA didn't work. So MAGMA couldn't compute the Betti numbers that we needed. Even if we were already like working over modulo P. So we took primes of good reductions, and then the Betti numbers are the same thing. So we are allowed to do that. So even working like, with a small prime, Magma was not able, like in a reasonable amount of time, to tell us the value of the Petit numbers. But, however, we were able to use the Atkin-Lerner test, like in a little bit more complicated way, but like by considering like some quotients, because they are modular curves, so we have these nice involutions. So we were able like to make the quotients, and then we could compute equations of these quotients thanks to this algorithm, and then we could say something about the gonality of those quotients and use that to get a contradiction. So then we were able to handle like all those cases, except 4. So, I can say that all those cases, actually, there were 23 here and 55 here. So we were able to remove like all cases except 4. So now the theorem, and I'm really done stating this theorem, that we can prove, improving a little bit the first theorem that I wrote there, is the following. There is no modular curve of Shimura type which admit a smooth plane model of degree 5, 6, 7, and if it admits such a model of degree 8, then it is isomorphic to one of 4 curves that are the 4 curves that we found there. So this is, after that theorem, our next theorem, and this is everything that I wanted to tell you. Thank you very much for your attention.
Any questions for the speaker?
Why would you want a modular curve to be of Shimura type? What if it isn't? Is that a problem?
At least it's defined over the rational, so this is a nice property. There are so many other ones. Other precise applications.
It looks a bit like a random definition to me. I don't want to complain again, but
it's a very legitimate question. So basically, the thing, as I said, is like there are many congruent subgroups, so we couldn't check for all of them. You just have to restrict yourself to some. That was the philosophy. You do what you can, and what you can is like restrict yourself to a family. And then we took this family precisely because Eran had been working on this algorithm on the implementation, and he was focusing on this family. So the algorithm was working perfectly for this family. So it was, let's take this family. But besides that, there is no other motivation.
There's no higher mathematical reason. It's just to restrict the zoo a little bit.
Yeah.
Okay, thank you.
Yeah.
I actually don't have a question. I have a comment to answer Peter's question.
Perfect.
So the modular curves of Shimura type are exactly the ones that are going to show up as parameterizing Galois images, Galois representations of elliptic curves over Q. And I think that's an interesting arithmetic reason to be focusing on these particular cases. So this is constrained by having the surjective determinant, insisting that -1 be there is only is a minor constraint that will tell you that you can always twist your elliptic curve to achieve that image. So modulo parameterizing twists, you're going to get everything that you would ever see arising from an elliptic curve, where an elliptic curve over Q would be a point on your potential point on your modular curve.
Much better answer. Thank you very much.
Yes, because we're being recorded, and then. So I think I also have a comment in response to Peter's question. Am I right in thinking that the groups of Shimura type, they're the ones where you have heck operators and DAC and linear involutions, and that makes it very much easier to find the Q expansions.
This is maybe why the algorithm works better in this case.
Yes, absolutely. I mean, if you ever want to find an equation for something that isn't of this type, you have to work quite a lot harder. Yeah.
What would you need to do to plausibly either rule out or rule in those remaining 4 cases for degree 8?
Thank you very much. I was waiting for that question. So I can tell you.
You're welcome.
Actually, so I mean, I said that the Cummins-Pauli list goes only up to genus 24. But actually, I mean, after getting the paper published and accepted and everything, Martin Derricks contacted us and said, hey guys, I ran like code to compute the congruent subgroups of Shimura type up to the bound that you want. And even better, I also implemented your Atkin-Lennard test, like to remove, you do the Atkin-Lennard quotient, and if you get a hyperelliptic curve of a small genus, then because of the gonality argument, you remove it. So he called that the Atkin-Lennard test, and he ran all these for us, and basically he told us, okay, now I have only 11 curves. Everything, yeah, because here I was restricting myself up to Shimura type, but up to degree 18. That is really, I mean, the bound that we get in our theorem. So all of them. Yeah. So I mean, he did that, and there were 11 curves, and then he started with Eran actually to play a little bit to remove cases. Oh, but here we can do this. With this one we can do this. Blah blah blah. And the last update that I have in December is that they were able to remove all of them except 2 of them. Of degrees, I can tell you, one of degree 8 and one of degree 9. This is from December. So, I mean, the larger degree, actually the degree 18, for instance, I remove all of them. That this is somehow coherent with the remark about the dimensions, right? The larger the degree, the more difficult that you are going to get such a smooth plane model. So in December 22, there were only 2 curves left, Shimura type. So, I mean, I don't know, maybe by now, I don't think they are still done, but they are on the way like to really check all of them. Please. I like your questions.
Are the Betty numbers, so you couldn't do them in Magma, but are they the type of thing that, oh yeah, this should be way too intractable? Or is it just you'd have to write something that does it fast somehow?
No, I mean, honestly, I think that unfortunately the algorithm that we give here about, oh, you compute the Grady Betty number and then you use the Schreier thing like to compute the P2 is more of a theoretical algorithm. Like, I mean, it's not really Magma fault, okay, or the people that implement it. I mean, it's really that computing these Betty numbers is actually very expensive because you have to work like with Grosvenor basis. And I mean, suddenly the coefficients are huge. You have a lot of coefficients. I mean, because it's G, I mean, it's the D minus 1, D minus 2 divided by 2 variables. So no, I mean, the competencies are huge. So here I don't have that much hope that things can be improved.
Thanks.
Thank you.
So as Drew was saying, these curves you've been looking at are interesting from the point of view of Galois representations. Do you know if the rational points are known for all the curves you've looked at? And if not, would your models help?
I don't know. I mean, I don't know about the rational points. This is an interesting question. The only thing I can say about the models that we checked a little bit with the literature in previous things is like so many of the curves that we get here, of course, other people had, because I mean, we got models for all of them. For all these, I mean, with that algorithm, we get all the equations. They are available at Eran's website. And some of them were already computed by other people. And I mean, of course, we checked that we were getting like the same equations, so this is fine. But no, we didn't look at the question of rational points. But this can be very interesting, indeed. Thank you.
Any more questions?
Not a question, just a correction of my comment. I was responding to the statement that Elisa was pointing to, but the Shimura type does impose an additional restriction. For example, you're always going to have a rational anisogeny. But I think you could explain that condition in arithmetic terms, in terms of the torsion structure of the elliptic curve. But it is a proper subset of sort of the full universe you might want to think about, which would be everything with surjective determinant containing -1, which I think is a very natural family to consider.
Thank you. No, I'm taking notes about your comments also for the next time I give the talk, and I can reply better to this. But yeah, I mean, this is why in the table over there, I insisted on the real type and surjective determinant. And then, because I mean, this is where we can apply the algorithm, but then we restrict it a little bit more with the Shimura type. That, I mean, as you said, this is the isogeny that we see like on the shape of the matrices that we are considering.
Thank Elisa again.
Thank you.